There is a rock sitting on a hillside on the moon, and it should not be there. It is about 9 meters across, resting partway down the sloping wall of an old crater in the moon's far south. Behind it stretches a single clean track, pressed into the dust, running uphill, back the way it came. You can follow it with your eye. It looks fresh. A casual glance would swear the rock finished its journey last week. But nothing on the moon happens last week. This image comes from a camera aboard a NASA spacecraft circling the moon. And for years it was just one quiet photograph in an archive of millions of stone, and the trail it left behind when it moved. Then someone went looking for more. And only recently, poring over thousands of those same NASA images, researchers found the same thing again and again. 245 fresh scars where boulders weighing tons had rolled, bounced, and slid down crater walls not in the deep past, but within the last few 100,000 years. A blink on a world 4 billion years old. Here is the part that stops them cold. The moon is supposed to be finished. Dead rock. A fossil hanging in the sky, with nothing left to do but sit there and collect craters. Something is still moving things across its surface, and the people staring at the sharpest pictures NASA has ever taken cannot yet tell you what. So here is the question that pulls us all the way down to the surface tonight. If the moon died 1 billion years ago, then what is still pushing the stones? For most of the last century, the picture was simple. The moon formed, the moon cooled, the moon stopped. The interesting chapters were all in the deep past. What you saw through a telescope was the aftermath of a story that had already ended. That is the belief our whole tonight rests against. And it belongs, more than to anyone, to a quiet contradiction that came out of a laboratory in Ahmedabad, in India. His name is Siva Prahasam Vijayan. He is an associate professor at the Physical Research Laboratory, and he has spent a long stretch of his career doing something almost no one has the patience for. He sits with images of the moon, thousands of them, and he looks, not at the famous craters, at the slopes, at the faint scratches most people would never notice. And the thing he keeps running into is movement. For a long time, he has said, there was this belief that the moon is geologically dead. He says it the way you say a thing you no longer believe, because his own pictures keep arguing with it. Boulders with sizes running from tens of meters to hundreds of meters, with weights measured in tons, have shifted from where they were, not eons ago, recently. That is the human engine of this whole story. One researcher, with a quiet stubbornness, refusing to accept that the moon is finished and going through image after image to prove it. By hand. But to understand why a single track on a slope is such a big deal, you have to understand how much it takes to leave one. Now, the moon is a terrible place to hide a footprint, and a perfect place to keep one. Terrible, because the surface is constantly being chewed up. Micrometeorites, tiny grains of rock, moving at enormous speed, fall endlessly, turning fresh ground into churned ground. Scientists have a quiet word for it. They call it gardening. The soil gets turned over and over, mixed up and down by an unending drizzle of impacts. Perfect, because there is nothing else. No wind to erase a mark, no water to wash it flat. So when something does happen on the moon, the surface holds onto it until the slow gardening finally wears it away. That tension is exactly what makes a boulder track useful. It is a clock. Here is how the clock works. When a boulder rolls down a slope, it presses a track into the regolith, and it kicks up fresh material from just below the surface. That fresh material matters. The very top layer of the moon is darkened over time, weathered by sunlight and solar particles, a process called space weathering. But the stuff underneath is bright and untouched. So a new track, freshly cut, shows up brighter than the old grey around it. A faded track has had time to darken back down, so you can read the age right off the surface. The brighter the scar, the more recent the roll. And there is a finer trick still. As a boulder bounces and slides, it scuffs up a delicate fan of dust on either side of its path, a herringbone pattern, like the bones of a fish laid open. Researchers call it boulder fall ejecta. When that pattern is sharp and clear, the event was recent. When it has blurred away, the event was old. The pattern is the timestamp. Stack those clues together. The brightness, the herringbone, the crispness, and a scratch in the dust stops being a curiosity and becomes a date. But how recent is recent on a world that measures time in billions? The boulder in Schiller gives a first answer. Studies suggest the steady gardening of micrometeorites should erase a track like that over tens of millions of years. From the few small craters that sit on top of the track and therefore came after it, we know the rock has been still for a while, but not forever. The best estimate is that the track is no older than 50 to 100 million years. On a 4 billion-year-old world, that is the difference between an ancient ruin and a fresh scuff on the floor. And here is the part to sit with for a moment, because it is the heart of everything that follows. The rock in Schiller did not have to move in the deep past. It moved in geologically recent times. Something disturbed it long ago to us, but barely yesterday to the moon, and sent 9 meters of stone rolling down a slope on a world we had written off as motionless. And then it stopped, in a spot where the ground levels out, where it is unlikely to roll again. The track is the only evidence it was ever in motion at all. One stone could be a fluke, so let's see how many there are. For a long time, the answer was, we don't really know, because we could barely see them. The early track hunters worked from old orbital photographs, and the problem was resolution. Less than 1% of the lunar surface had ever been imaged sharply enough to pick out something as fine as a boulder track. You needed detail down to a few meters per pixel. Most of the moon had never been seen that well. So the tracks that were catalogued were a scattering, a few here, a few there, hand-logged with crude codes and frame numbers, more like a rumor than a map. Then the sharp eyes arrived in orbit. NASA's Lunar Reconnaissance Orbiter, with its narrow-angle camera, began returning images detailed enough to resolve the tracks clearly, and suddenly there were a lot of them. People combing the new pictures realized the number of boulder tracks on the moon was not small. It was enormous. And that sets up the discovery that brings us right up to the present. Vijayan and his colleagues took on the slow work. They manually searched thousands of images of the lunar surface, concentrating on the band that runs between 40 degrees south and 40 degrees north, the middle latitudes, where the sun strikes at angles that make the bright tracks stand out from the gray. Whenever they found one, they pulled the matching high-resolution images from NASA's orbiter, taken across the years from 2009 to 2022, and studied them. Then they did the thing nobody had done before. They didn't just spot the tracks, they located them precisely, and they dated them. The result was published in the late summer of 2025 in a journal called Icarus, and the number is the thing to let sit. 245 fresh boulder tracks. 245 places where a boulder rolled, bounced, and slid down a crater wall recently enough to still show a bright, sharp scar. Not relics. Recent events, scattered across a world that was supposed to have nothing left to do. Let that land for a second. Because the easy thing is to hear a number and move on. But every one of those 245 scars is a moment of motion on a dead world. Every one is a stone that was sitting still and then was not. 245 times, the moon moved and left the evidence lying in the open for anyone patient enough to look. To pin down how recent, the team leaned on the most reliable clock the moon offers: impacts. When a meteorite hits, it throws out a blanket of debris, an ejecta blanket, and those blankets have been used for decades to estimate the age of an event. They have a nickname. People call them the lunar equivalent of fossils. By studying regions where boulder tracks sat alongside the debris blankets of nearby craters, the team could bracket the timing. The craters they analyzed came out to around 400,000 years old, which means the boulder tracks beside them are younger still. 400,000 years sounds like an eternity. On the moon, it is practically now. Modern humans were already walking the Earth. And in that window, a blink, By lunar standards, boulders weighing tons were getting up and moving. So we have the movement. We have the timing. There is only one thing left, and it is the thing nobody can hand you cleanly. What is pushing them? Here is where the calm part of the story has to admit something. We can see the tracks. We can date the tracks. We cannot, yet, say for certain what made them. There are really only two candidates, and the whole investigation comes down to telling them apart. The first candidate comes from outside, an impact. A meteorite strikes nearby, the ground heaves, and a boulder that had been balanced on a slope for ages is knocked loose. Or a small meteoroid hits the boulder directly and sends it tumbling. Scientists call these outside causes exogenic, driven by something arriving from space. The second candidate comes from inside, a moonquake. The moon, it turns out, is not perfectly silent in its depths. The ground can shake, and a strong enough tremor could shrug a boulder off its perch just as surely as an impact. Causes that come from within the moon itself are called endogenic. So a boulder track is a confession that something happened, but it doesn't say who did it. The same scar could be written by a hand from space or a hand from below. And the mechanics, once a boulder is moving, are almost gentle to watch. A boulder on a slope is extremely sensitive to inertia. Once it is knocked loose, it simply keeps going until something changes its motion, until the slope flattens, or it strikes a ridge, or the ground grabs it. Most tracks run more or less straight, a dashed line from high ground to low. But not all of them. In one place on the lunar far side, near a worn-down crater called Pikel'ner, there are tracks that curve. 4 boulders, ranging from about 7 to 9 meters across, ran down a slope along smooth, sub-parallel arcs that bend with the land. Look closely, and you can read the story in the curves. These boulders were almost certainly flung out of a fresh impact crater nearby, thrown across the landscape, and dropped onto the worn inner wall of the older crater, where they then rolled downhill, their paths bending to follow the local slope. There is even a tell in the tracks themselves. They are continuous and smoothed, like a marble rolled down a pile of sand, not broken and disconnected, like a marble bounced down the same pile. And the small wiggles along the way, those are just the boulders being boulders. Real rocks are not perfect spheres, so they wobble as they go, and the wobble gets pressed into the dust. Now, here is the quiet thing to tuck away, because we are going to come back to it. Every one of these explanations, the impacts, the moonquakes, the curving paths, is about big solid objects. Stones you could see, stones you could stand next to. But the people studying the moon keep using a strange word when they describe what disturbs the surface. They talk about charge, about particles sticking where they shouldn't, about dust that does not behave the way dust on a dead world ought to. Hold that thought. The boulders are not the only thing on the moon that moves. Because the tracks are also doing something useful while we puzzle over them. The dimensions of a track, set against the size of the boulder that cut it, reveal how the ground responds to a load. A boulder sinks deeper into soft material than stiff material. So, from the depth and shape of a track, researchers can measure the bearing capacity of the soil, its ability to hold weight without ever landing a spacecraft there. That matters more than it sounds. There are places on the moon that no astronaut and no rover has ever crossed, pyroclastic deposits laid down by ancient volcanic fountains, and the permanently shadowed regions near the poles where sunlight never reaches. We have no idea how firm the ground is in those places, and that is not a small worry. Soft soil has caused real trouble before it complicated operations on Apollo and on the Soviet Lunar rovers, and on Mars it swallowed a NASA rover whole and never let it go. A vehicle that sinks too far is a vehicle you lose, so the boulder tracks are doing double duty. They are evidence that the moon still moves, and they are a free survey of ground we have never touched, scouting the way for whatever we send next. But to find out who is pushing the boulders, the researchers all say the same thing. And it is humbling. We need more ears. To tell a moonquake from an impact, you have to feel the ground shake at the moment it shakes. That means seismometers, and not one or two. As one scientist who studies these falls put it, what's needed is a large network of seismometers covering the entire moon, listening continuously for decades. Only then can you stand over a fresh track and say, with confidence, whether the push came from the sky or from below. Until then, the tracks remain what they are: proof of motion with the cause left blank. And if that were the whole story, it would already be enough. But the boulders are the loud evidence, the strange evidence, the evidence that genuinely stopped scientists in their tracks is much smaller. It is the dust. Let's go back to December of 1972, to the last time human beings stood on the moon. The crew of Apollo 17 left something behind in the grey dust of the Taurus-Littrow Valley. A small instrument with a plain name, the Lunar Ejector and Meteorites Experiment. Most people just called it LEAM. Its job was simple and specific. It was built to catch the tiny particles thrown up when small meteoroids slam into the moon. It had 3 sensors, one facing up, one facing east, one facing west, and each could record the speed, the energy, and the direction of the little grains that struck it. Point it at the sky, wait for the dust of impacts to come down, count what arrives. That was the plan. The moon had other ideas. LEAM did not mostly see particles coming down from above, as expected. It saw a flood of particles every morning, and they came from the sides, from the east, or from the west, not from overhead. And they were moving too slowly, slower than the speeds you would expect from material flung up by an impact. Whatever this was, it was not the gentle rain of debris the instrument had been designed to catch. It was something moving sideways across the surface, in step with the rising sun. That alone was strange. But then the instrument did something stranger. It began to overheat. A few hours after each lunar sunrise, LEAM's temperature climbed toward nearly 100 degrees Celsius, so high that the unit had to be switched off temporarily just to keep it from cooking itself. Every lunar morning, the same thing. The sun would rise, the sideways particles would pour in, and the instrument would start to burn. So what was happening? The leading idea is almost eerie. The thought is that electrically charged moon dust was sticking to LEAM, coating it, darkening its surface. And a darkened surface stops reflecting sunlight and starts absorbing it. The instrument was being slowly painted black by the very dust it was trying to measure, until the morning sun could no longer be shrugged off, and the heat built and built. Now here is the line that matters, and I want to give it to you plainly, because it is the honest center of this whole subject. Scientists were unable to make a definite explanation of the problem. They tried. But LEAM operated only briefly before the Apollo program ended, and the experiment was switched off for good before anyone could get to the bottom of it. The data sat there, a flood of slow, sideways particles every dawn, an instrument that kept blinding itself with dust, and the explanation never came. It is one of the cleanest examples on the moon of a thing observed, measured, recorded, and never resolved. So what could possibly throw dust sideways across an airless world every single morning with no wind to carry it? The answer that scientists keep circling is not wind, it is electricity. To understand how dust could move on its own, you have to throw out everything that moves dust on Earth. On Earth, dust travels because something pushes it. Air, water, a gust, a current, a hand. The moon has none of that. And yet there is real evidence that the moon carries a thin layer of moving dust particles leaping up from the surface and falling back over and over, so that the whole faint layer looks frozen while it is actually in constant motion. It even has a name that captures it perfectly: the moon fountain. The same way a fountain on Earth looks like a solid shape. While every drop in it is racing up and falling back, the dust seems to hang there, static, while each grain is in flight. And the engine, the thinking goes, is charge. Walk through it slowly, because this is the mechanism that ties the whole night together. On the daylit side of the moon, The sun pours out hard ultraviolet light and X-rays radiation, energetic enough to knock electrons clean out of the atoms in the surface dust. Strip away electrons, and you leave a positive charge behind. The grains build up that positive charge until the tiniest of them, the ones a single micrometer across and smaller, are repelled from the ground beneath them, like the wrong ends of two magnets shoved together. And they lift. The smallest grains can be thrown anywhere from a few meters to kilometers high, with the very smallest reaching the very top. Then they lose their charge, fall back, and the whole cycle begins again. The night side is stranger still. There, the dust is charged the opposite way, loaded with electrons delivered by the solar wind, the stream of particles flowing constantly off the Sunday. And the models suggest the night side can build up an even greater electrical tension than the day side, which means the night side might be flinging dust to even higher altitudes than the morning ever does. And then there is the seam between them, the line where lunar day meets lunar night, called the terminator. Right along that boundary, day-charged ground sits next to night-charged ground, and between them, strong horizontal electric fields could form. Fields that would not lift dust straight up, but drive it sideways, push it across the surface, from the lit side toward the dark. Stop there for a second, because that is exactly what Lehm saw. Slow particles, moving sideways, arriving every morning as the terminator swept across the valley. The fountain model has a word for this terminator-driven, horizontal movement of dust. It calls it a moonstorm. This is the kind of idea that sounds like science fiction, and, in a way, it once was. The whole effect was anticipated back in 1956 by a science fiction author named Hal Clement in a short story called Dust Rag, printed in a magazine of the era. He imagined charged lunar dust before the instruments ever found it. Decades later, in 2005, a research group at a NASA laboratory put forward a serious model of electrostatic levitation that gave the fiction a physical backbone. And there was older evidence still, waiting in the photographs. Back in the 1960s, the Surveyor spacecraft that soft-landed on the moon returned pictures of something that should not have been there. A twilight glow hanging low over the lunar horizon, lingering after the sun had set. On a truly airless world, the line between ground and black sky should be razor-sharp. It wasn't. There was a faint brightness clinging to the horizon, the kind of glow you get when sunlight scatters off a cloud of suspended dust. The crews saw it too. The Apollo 17 astronauts orbiting the moon repeatedly saw and sketched what they called bands, or streamers, or twilight rays visible for about 10 seconds just before lunar sunrise or sunset. Crews on Apollo 8, Apollo 10, and Apollo 15 reported the same. Faint rays of light at the edge of a dead world, looking unsettlingly like the rays our own atmosphere throws at dusk, and the lab work seemed to back it up. In a study published in 2017, researchers showed that under ultraviolet light or exposure to charged gas, micron-sized dust grains really could jump, lifting several centimeters off a surface. On the moon, that same effect, they calculated, would loft particles more than 10 centimeters high. Enough, perhaps, to explain that stubborn glow on the horizon that Surveyor caught 5 decades before. It all fit. The fountain, the storm, the glow, the sideways dust at dawn, a moon quietly alive with charge, its surface in slow, electric motion. And then we went back to check, and the moon refused to cooperate. This is the turn in the story, and it is the most honest part of it. Because the satisfying thing would be for the careful new missions to find the fountain and close the case. They didn't. In 2013, NASA sent a spacecraft to the moon built to do exactly this kind of search. It launched in early September and slipped into lunar orbit about a month later. On board was a dust detector designed to hunt for the lofted grains directly to fly through the region just above the terminator, where the fountain should be densest, and feel for them. It looked across a band of altitudes, from a few kilometers above the surface up to a couple hundred. And within the limits of what it could detect, it found no evidence of electrostatically lofted grains over the terminator. None. The numbers it set as an upper limit came out 2 to 3 orders of magnitude below what the old Apollo-era observations had led everyone to expect. The fountain, if it was there at all, was far, far thinner than the glow had promised. That same year, another lander put the question to the surface itself. China's Chang'e 3 launched in early December of 2013 and set down a couple of weeks later in a vast lava plain called Mare Imbrium, the first soft landing on the moon since the Soviet Union's last robotic mission, all the way back in 1976. It carried a small, clever instrument, a solar cell that could double as a dust detector. The logic was simple. If charged dust really lofts and settles, it would gradually coat the cell, and the cell's output would fall in a telltale way. The lander even got a rare gift. During its mission, the moon passed through 2 total lunar eclipses, and an eclipse is like a sped-up sunrise and sunset, the sharp boundary of light and shadow sweeping across the surface twice in a short span. If the fountain existed, if charged dust really surged at that boundary, the eclipses should have driven a pulse of it right onto the detector. The dust never came. After the first settling the unavoidable mess of landing and a rover's wheels stirring up the surface, the cell did not behave the way the fountain model predicted. There was no sharp surge of lofted dust over the following lunar mornings, and when the sharp shadow boundary of each eclipse swept across the site, there was no abrupt jump in dust either. Within the instrument's reach, the dense cloud of charged dust that the Apollo era had imagined over the Terminator simply was not there. So what does that mean? It does not mean the dust never moves. The careful conclusion is more interesting than that. It means the lofting mechanism is weaker than people once thought, too weak, in most places, to overcome the forces holding the grains down. Lunar dust is sticky. The grains cling to each other with what scientists call cohesion, and they are pinned by the moon's gravity. And it turns out the electric repulsion between like-charged grains is usually too feeble to break them free entirely. And there is a quiet detail that keeps the door open. The landing site in Mare Imbrium is geologically young, with relatively weak dust activity to begin with. It may simply be a calm neighborhood. The fountain might still run in other places, or it might run only very close to the surface, lower than the instruments could see, in a thin layer hugging the ground, below the reach of the detectors looking down from above, which leaves us in a peculiar and very real position. We have an instrument from 1972 that flooded with sideways dust every morning and cooked itself, and could never be explained. And we have careful new searches that went looking for the dust and largely came up empty. Both are true. Both are the actual record. The moon gave us a clear signal, and then, when we returned with better tools, mostly took it away again and never told us why the first signal was so loud. The movement on the moon is real. The explanation for it keeps slipping between our fingers. And if you think that is a modern frustration, you should know that people have been chasing lights on the moon and failing to explain them for a very long time. To see how old this puzzle is, set down the instruments and pick up the historical record. Because long before any spacecraft, people on Earth kept seeing the moon do things it was not supposed to do. They have a name now. Transient lunar phenomena, short-lived changes in the brightness, the color, or the appearance of a patch of the moon's face. The term was coined by the British astronomer Patrick Moore in a NASA technical report published in 1968, but the sightings go back far further than that. Claims of these fleeting events stretch back at least 1,000 years, and the catalogues of them now run to more than 2,000 entries, reaching all the way back to the 6th century. They are not all the same. Some are sudden flashes. Some are slow, amorphous glows, reddish or whitish, or a hazy darkening that shifts shape and then fades over seconds or minutes. And they cluster. Of the most reliable of them, A striking share, at least a third, come from the same small region, the vicinity of a single bright crater called Aristarchus. The oldest famous account is genuinely strange to read. On a June night, in the year 1178, 5 or more monks in Canterbury, in England, reported that the upper horn of the new crescent moon suddenly split, and that from the division a flaming torch sprang up, throwing out fire and sparks, while the body of the moon below seemed to writhe. For a while, scholars wondered if they had witnessed the birth of a crater. More recent work suggests that is very unlikely. An impact big enough to carve that crater should have rained debris on the Earth for a week, and no such storm appears in any record we have. The likeliest answer is that the monks happened to catch a meteor exploding in our own air, by chance lined up with the distant moon. That is the trouble with these lights. For every one, there is a sky's worth of explanations, and very few of them can be pinned down. But the sightings never stopped. They ran straight through the centuries, through famous astronomers and amateur observers alike, and right into the space age. And one of the most remarkable came at the most remarkable possible moment. In July of 1969, with Apollo 11 inches orbit around the moon, ground-based observers in Germany reported a glow near Aristarchus. The report was relayed to Houston, and Houston radioed it up to the crew, asking them to take a look. And Neil Armstrong, a day before he would become the first human being to walk on another world, looked north toward Aristarchus and answered. He said there was an area considerably more illuminated than its surroundings. It seemed, he said, to have a slight amount of fluorescence to it. Michael Collins and Buzz Aldrin saw it too, a patch of the crater's inner wall, brighter than anything else in view. 3 astronauts, looking at the same crater, agreeing that one piece of it was glowing. And still, no one can say for certain what it was. So what could be lighting these patches? Over the years, the explanations have sorted themselves into 4 families, and it is worth knowing them, because every one of them ties back to something we have already met tonight. The first is outgassing gas escaping from beneath the surface, stirring up the dust or catching the light. There is real support for it. Instruments on Apollo and on a later orbiter detected radon gas, a product of radioactive decay leaking to the surface, and leaking most strongly from the very regions where these lights are most often reported, including Aristarchus. The places that glow and the places that breathe gas line up. The second is impacts meteoroids striking the moon, each one a brief, bright flash. This one is not in doubt at all anymore. From 2017 to 2023, a dedicated survey watched the moon and recorded nearly 200 separate impact flashes. And the brightest lunar flash ever caught, back in 2013, was later matched to a fresh crater about 35 meters across, photographed by NASA's orbiter, a before and after picture of a scar being born. The third family is electrostatic, the same charged dust effects we have been chasing all night. The idea that charging and discharging of the surface, or the levitation of dust near the terminator, could throw light visible from Earth. The fountain, reaching all the way back across the void to flicker in a telescope. And the fourth, the humble one, is us, our own atmosphere. Many of these lunar events may never have been on the moon at all, just our turbulent air smearing and shifting the image, or a satellite, or a meteor, or simple human error at the eyepiece. That is the honest spread of it. Some of these lights are surely real and tied to the moon. Some are surely tricks of our own sky. And teasing the two apart, over 1,000 years of mostly single-witness reports, is one of the hardest things in all of lunar science. But the flashes, at least, have stopped being a mystery, and they have come right up to our own moment, because the most recent confirmed sighting came not through a telescope, but through a window. Bring it all the way forward to this year. On the 6th of April, 2026, 2 astronauts named Reed Wiseman and Jeremy Hansen were flying past the moon aboard an Artemis mission, and they were passing through a total solar eclipse as they went. And each of them, independently reported seeing 3 flashes on the surface below. NASA described them plainly: impact flashes. Light created by meteoroids striking the lunar surface, the same phenomenon people had been squinting at for centuries, now witnessed up close by human eyes in passing. There had even been a call beforehand for people on Earth to watch for impact events at the same time, turning ordinary observers into a network of witnesses. It is a small thing and an enormous thing at once. 1,000 years after the monks of Canterbury wrote down a light on the moon they could not explain, 2 astronauts watched the same kind of light flicker beneath them, and this time we knew exactly what it was: a rock hitting the moon, throwing off a spark of its own destruction. That is the shape of the whole subject in a single arc. The lights we have learned to explain, we have explained. The flash of an impact, the birth of a crater photographed before and after. The slow scar of a boulder dated against the fossil blankets of nearby craters, but the deep emotion, the dust that moved sideways every morning and was never understood, the fountain that the glow promised and the detectors could not find, the hand that pushes the boulders down the slopes, whether it reaches in from space or up from below that, we have not closed. So let's step back, all the way back, and look at what we actually have. Here is what we know for certain. We know that boulders weighing tons have rolled across the surface of the moon within the last few 100,000 years, a fact written in 245 fresh scars, read out of NASA's orbital images by people patient enough to find them. That is not a hypothesis. The tracks are there. We know that an instrument left on the surface in 1972 recorded a flood of slow, sideways dust every lunar morning and blinded itself with that dust until it overheated. That is not a hypothesis either. It is in the record. What it means is the part no one could ever pin down. We know there is a faint glow that clings to the lunar horizon at dawn and dusk, seen by spacecraft and sketched by astronauts, that looks for all the world like sunlight scattering off suspended dust. And we know that for at least 1,000 years, careful people have watched patches of the moon brighten and redden and fade, and that the places they glow line up uncomfortably well with the places the moon leaks gas. Now here is what we do not know. We do not know whether the boulders are pushed by moonquakes from within or by impacts from without, and to find out, we would need to wire the whole moon for sound and listen for decades. We do not know why Liam saw what it saw, and we never will from that instrument, because it was switched off before the answer came. We do not know why the dust fountain that the glow seemed to promise was missing when we finally flew through the place it should have been, only that the force lifting the dust is weaker than we thought, and the grains cling harder than we expected, and the whole thing may run only in a thin layer too low to see. So, consider where that leaves the old, comfortable picture. The moon as a finished thing, a fossil, a dead grey stone that does nothing but hang there and collect craters. It was never quite true. The boulders move. The dust leaps and falls and drifts sideways at dawn. The horizon glows. The surface flickers with lights we are only now learning to name. The moon is not doing nothing. It has been quietly in motion the whole time, turning its soil, charging its dust, dropping its stones down its slopes, and we simply could not see it well enough to notice until the cameras got sharp and someone sat down to look. And maybe that is the part worth carrying away from all of this. Not the answer. We don't have the answer. What we have is the better question and the strange humility of standing on a world that everyone agreed was dead, watching it move and realizing we cannot yet say why. We built the cameras, we flew them to the moon and put them in orbit. We caught the stones in the act of having moved, and the dust in the act of having jumped, and the light in the act of flickering on a face we thought had gone, still 1 billion years ago. And for all of it, all the instruments, all the missions, all the centuries of watching the moon is still keeping the best of its secrets just out of reach, 400,000 years and one unanswered question away. For now, all we can do is keep looking, and the longer we look, the less dead it seems.